we need to estimate now the incident energy on a tilted surface with atmospheric effects. So let us draw the real physical setting on how the collector is placed and what are the various radiation and atmospheric effects that comes into picture. So for that, let me draw the ground profile. This is the ground profile. There is a hilly region here, and then the valley region where probably we will place the flat plate collector at an angle, and this basically is our ground surface. Now on this ground surface, let me place a flat plate collector, and that flat plate collector is kept in inclined manner like this, mounted onto struts, and it is at an angle beta to the horizon. Beta is the tilt angle. So this could probably be a PV panel flat plate collector. Now to this PV panel flat plate collector, our objective or the goal is to find out what is the amount of insulation that is falling on it, and to calculate the daily incident energy on this flat plate collector panel, which includes all atmospheric effects. Now consider a line like this, and this line is supposed to represent the outer atmosphere. So we will call this as the atmosphere boundary. Now from the distant sun, we will have an insolation vector falling onto the flat plate collector, and this is called the direct insolation vector, and this is coming directly from the sun. So this is the direct incident radiation falling onto the panel. Apart from this direct incident radiation, there are other forms of radiations, subsidiary forms, and one of them is, let's say I take another parallel insulation line which is falling on the nearby neighboring hill, slope of the hill. So what happens after it falls on the ground, gets reflected, and it get reflected in multiple directions, and these reflected radiation can also go and fall on the flat plate collector and affect the amount of collected energy at the panel. Now this ground reflected radiations are called albedo. The term albedo is used for ground reflected radiations. So you see that there is this direct insolation falling on the flat plate collector, tilted, and then there is this albedo effect also, ground reflected effect also coming onto the collector. And apart from that, there is one more important effect that comes into picture, and that is the diffused radiation. You will see that there is cloud cover, and the insolation that is directed towards the flat plate collector will get scattered and will also get diffused due to the cloud, and you will see that there will be many insolation vectors in different directions pointing, and many of them pointing towards the collector in this fashion, and this is called the diffused radiation. And it is our objective to find HAT. HAT is the energy incident on the flat plate collector, which is tilted at an angle beta, including the atmospheric effects. That is what HAT means. And HAT is actually a composition of energy from direct radiation plus energy from diffused radiation, like this, plus energy from reflected, ground reflected radiation, or the albedo. So all these three effects put together is what will be the HAT, or the energy available at the tilted flat plate collector as positioned like this. Now this is a practical and real situation. How do we go about estimating this? There are so many uncertainties in this. Unlike in the previous cases where we found HO, H naught and H naught T, energy incident on a horizontal flat plate collector and energy incident on a tilted flat plate collector without the effect of the atmosphere. That was a much more idealistic and deterministic relation that we arrived at. But here it is not so deterministic because we don't know the climatic condition at the locality. This would mean that we don't have the exact accurate model for predicting the cloud nature, the nature of the water vapor and other gases content in the vertical column above the collector. All these knowledge is not available in any model form, and we only have knowledge of history. We only have statistical data, and based on the statistical data only we can arrive at an approximate model which will try to give you an approximate value for these, and give you an estimate of the energy that will become available at the flat plate collector. So let us try to see how we can get as best a value for this HAT in the discussions to come further. Let me now explain tilt factor, the concept of tilt factor without atmosphere. You see, we have already found out the energy that is incident on a horizontal surface and on a tilted surface without atmosphere. So with respect to those energies, let us define this term RD. RD is called as the tilt factor of the direct radiation. RD is called the tilt factor of the direct radiation, and it is defined as the daily energy on tilted surface to the daily energy on horizontal surface. This is without the atmospheric effects, and this is equal to, we know how to calculate daily energy on tilted surface. We have seen that, which is H naught T, and on the horizontal surface, which is H naught. So if you write down the equations of these two and cancelling the common terms, you will get cos phi minus beta cos delta sin omega SRT, sunrise angle of the tilted surface, plus omega SRT sin phi minus beta sin delta, divided by cos phi cos delta sin omega SR plus omega SR sin phi sin delta. Now we can simplify this slightly. Cos phi minus beta into cos delta, you take it out from the numerator. Cos phi and cos delta, take it out from the denominator, and you will get in the numerator sin omega SRT plus omega SRT tan phi minus beta tan delta. This is because you have removed cos phi minus beta cos delta. It will get divided by cos phi minus beta and cos delta. That will become tan phi minus. Likewise, on the denominator side also, you will get sin omega SR plus omega SR tan phi tan delta. Of course, we can cancel out cos delta here. Tan phi tan delta is nothing but minus cos omega SR. Tan phi minus beta tan delta is nothing but minus cos omega SRT. Substituting this, we can write it as cos phi minus beta by cos phi sin omega SRT minus omega SRT cos omega SRT by sin omega SRT minus omega SR cos omega SR. So this is defined as our tilt factor without the atmospheric effects. This is for the direct radiation without the atmospheric effects. We will have another tilt factor coming with atmosphere effects. So try to distinguish the two. Consider the direct radiation, where we will consider a flat plate collector that is placed horizontally like this, and normal to it there is the incident irradiance. Now we know what H naught is. H naught is actually the energy incident on this flat plate collector without atmosphere, and HA is the energy collected with atmospheric effects. HA of course is smaller than H naught, because HA is the attenuated value of H naught after having gone through the atmosphere. Now let us define a term KT. KT is defined as HA, the energy collected on a flat plate collector with atmospheric effects, divided by H naught, the energy incident on the flat plate collector without atmosphere or the atmospheric effects. And this is called clearness index. This is a very, very important factor, this clearness index, because this consolidates all the uncertainties of the climate. It includes, because it is the ratio of energy incident on the same flat surface with atmosphere divided by 1 without atmosphere. So this ratio kind of encompasses all the uncertainties, unpredictabilities, and the statistical nature of the information that is present in the climate at a locality. So this includes and incorporates all the statistical effects due to atmosphere. So this is a pretty important parameter which we will use, and we will discuss later how we will estimate this clearness index value from the previous historical data. For now, let us consider this as a variable and let us consider that this is estimatable. Now once you have this clearness index, then we can say that energy incident on a flat surface with atmospheric effects is equal to KT clearness index into H naught, the energy that was incident on the flat surface without atmospheric effects. Now what is HAT? HAT is the energy incident on the flat surface with atmospheric effects with a tilt of an angle beta, and this can be obtained by this ratio. HAT by HA would be same as HOT by H naught. Their atmospheric effects in both these cases will cancel out, and therefore HOT by H naught would also approximately will actually be equal to the RD which we just now calculated. This is the tilt factor of the direct radiation. Therefore, I will now say HAT is equal to HA into RD. This is an important relationship. Now this relationship, we shall now expand to include the diffused portion of the radiation and the reflected portion of the radiation, that is the albedo effects. But remember that both the diffused radiation and the albedo are again very uncertain parameters, varies from place to place, very difficult to have a closed form solution. So we will only be using a empirical relationship. So we shall expand this to include the empirical relationship of the diffused and also the reflected components into HAT. So now RD into HA can be expanded to KT into H naught. Now let me say HAT, and HAT is composed of the direct component HA into RD. Now this HA into RD, which is having KT into H naught, HA is KT into H naught. A part of this KT into H naught is going off into the diffused radiation. So I will have to subtract from this the diffused component, and I will deal diffused component separately as a separate term. So let us remove the diffused component from this. So I will say minus HD. Let us say HD is the diffused component of the air radiation, and into RD. So this part I will remove, HD into RD, the diffused component, and I will call this as the direct portion, and the diffused portion I will deal separately, and I will call that one HD into, now here an empirical parameter comes in which is dependent on the tilt angle. So 1 plus cos beta by 2, this relationship is an empirical relationship which deals with the diffuse component. Plus let us include the reflected component also. So it is a small fraction of HA. So in this rho is called the reflection coefficient. It is a value smaller, much smaller than 1, and 1 minus cos beta by 2. This is the reflected part, and this is also an empirical relationship, and it goes by this argument. See, when the tilt is 0, means when you keep the flat plate horizontal, beta is 0. So 1 minus 1, so there is no reflected component on a flat plate collector which is placed horizontally. So that is the argument with which this empirical relationship has been brought about. Rho is a reflection coefficient. It actually depends upon the terrain. If it is a plain terrain, if it is in the plains where there is not much possibility of reflection from the neighborhood ground surface, then rho is very small, around 0.1. And if you have a lot of mountains in the neighborhood, let us say the collector is placed in a valley and there are a lot of nearby mountains and slopes which can reflect a lot of light onto the panel, or if it is a snow-capped mountain which can reflect quite a significant amount of light onto the panels, collectors, then the reflection coefficient rho is 0.7 here. So you see that there is a lot of empiricalness which is brought into this relationship, but you cannot help it because of the uncertain nature of the locality and the climate. However, you should note that the direct portion is the dominant component of HAT, of the total incident energy. The diffuse and the reflected component will be the subsidiary components which will supplement the direct component. So give a lot of importance to this portion of the equation. The other empirical portions of the equations are added to make HAT much more closer to the practical value, much more accurate to the practical measured values. So then we can simplify this. I will put it as 1 minus HD by HA into RD, that is the direct portion, plus I will put HA into HD by HA 1 plus cos beta by 2, diffuse portion, plus HA into rho 1 minus cos beta by 2, this is the reflected portion. So I have HA as common factors. I can take out HA as a common factor and say HA into RT. Now where this RT is the overall tilt factor, taking everything into consideration, and HD by HA, the ratio of the diffuse to the energy with atmospheric effects on the horizontal surface, is again an uncertain thing, and it is also a Kerfit equation, again obtained from previous statistical history, and a Kerfit relationship is available for that, and I will write it down: 1 minus 1.13 times kT. It is, note that it is dependent on clearness index kT, which means this is a term which will vary with the climate, which will vary with the region, which will vary with the atmospheric effects on the vertical column above the collector. So there are a lot of uncertainties in this relationship, but it will serve the purpose for us for designing and sizing the PV panels. So this is a Kerfit relationship. And also note that rho, the reflection coefficient, is a value between 0.1 and 0.7, as we just now discussed. We have gone through a lot of steps to estimate the daily incident energy on a collector. We have derived equations, and we have formed relationships, and we have also stated some empirical relationships in order to estimate the daily incident energy on a horizontal flat plate collector, on a tilted flat plate collector, and also on flat plate collectors, tilted flat plate collectors with atmospheric effects. Now finally, to size the photovoltaic panel, you need this value HAT, the daily incident energy that a collector will collect, a flat plate collector will collect with atmospheric effects and with tilt. Now this is the parameter that we need to determine, and let us consolidate all the equations that we have derived and discussed by listing out the steps that will lead to this calculation. So first we start with the inputs, what you need. Determine the latitude at which the locality is placed and for which you want to calculate HAT, the day number, the day of the year on which you want to calculate HAT, and beta, the tilt angle. Now with these you can definitely estimate H0, which we have seen. We can also estimate HOT because we know the tilt angle, beta, and we need to estimate KT, the clearness index. This is the most important when you want to consider atmospheric effects, and KT is a function of latitude, the day number, the atmospheric or the climatic conditions at the day, on that day at the place. So it is a kind of a figure that will give you all the statistical history, which is based on all the statistical history of the place with respect to the atmosphere. So this is yet to be formulated. We need to discuss on this, but for now consider that KT can be estimated, and it is a dominant function of latitude and the day number. It can also be a function of latitude, day number and water vapor, but I will discuss that later. But for now, let us say KT needs to be estimated from these values, input values. Next, estimate or find out RD, the tilt factor for direct radiation, which is HOT by H naught. We have this and we can find this. Then estimate RT, which is the overall tilt factor, including the direct, diffused and the reflected radiation. And then finally you calculate the value of HAT, the important value of HAT, which is given by RT into KT into H naught. This we have seen just before. Shortly we discussed this one, and we need to calculate this, and this will be the value in kilowatt hours per meter square per day, and this is what you will use to size the PV panels. But before that, we need to do one important job. How do you find KT? We know how to find all other things. We know how to find H naught, HOT, we know how to find RD, we know how to find RT, and then this. Now this is the only parameter that we have not discussed, this clearness index. And how to find this clearness index? This is a statistical phenomena, and how does this clearness index factor encompass the entire climate of a particular locality? We will shortly see that.